Hello, everyone. This is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics. And this time I'm going to be talking about hypothesis testing and the one sample Z test. So, as previously mentioned, we have a null hypothesis, which is H0, written as H0, not HO, H0. And the null hypothesis basically says there is no effect slash no change. So nothing happened. So whatever the intervention is, nothing worked. Or if you're looking before and after, there was no change. So nothing really happened, and that's the opposite of what we want as a researcher. We don't want the null to be true or to be supported. We want the null to be rejected. And if we reject the null, we then support the alternative hypothesis, which is H1. And this basically says there is an effect slash change. There is some kind of change. Something happened. Now, that change can be in one particular direction or it can just be overall. So, this alternative hypothesis is also either directional or non directional. So, that alternative is going to be directional or non directional when we're comparing groups, right? Not all the time with every test, but when we're doing z-test or we're doing t-test, or we look at the binomial distribution, when we're looking at like differences between groups or difference between a group and a population, sample and a population, then we're going to look at either directional or non-directional. Directional, you're going to see words as greater, less, bigger, smaller, right? These are directional terms. This is also known as a one-tailed test because we're only looking at one tail. So we're either looking for greater or bigger, we're going to look to the right. If we're looking for less or smaller, we're going to look to the left. We're going to look in one tail of the distribution only. And that basically means that it's easier to reject the null with a one-tailed test because I only have to worry about one tail. I don't have to worry about the other tail. So therefore, it's easier to reject the null that way. And it's said to have higher power. We're going to talk about power afterwards. Non-directional, we're going to look for change. You'll see the word change. You'll see the word difference. You'll see effect. So we're not indicating the direction of the change, the direction of the effect. We're just saying that there's a difference, or there's a change, or there's an effect. And this is two-tailed because we have to look in both tails. It could be greater or less than. Two-tailed test. This makes it a bit harder to reject the null because we have to account for both tails. Now, we do not want to run a one-tailed test unless we are absolutely certain we know the direction of the effect. If we don't know if it's going to be greater than or less than, we just think it's going to be different, then you don't run a one-tailed test. You can only run a one-tailed test, a directional hypothesis test, when you are absolutely certain you know where the direction of the effect is going to be. So if I'm giving a drug to reduce anxiety, I'm expecting the drug to lower anxiety, so I know where to look. And therefore, a one-tailed test could be viable for that. But if I'm not 100% certain what's going to happen, if I do a different treatment and I don't know if it's going to increase or decrease whatever dependent variable I'm looking at, then we want to do a two-tailed test. So when in doubt, you always want to do a two-tailed test, a non-directional hypothesis test. For publication, the two-tailed test is I wouldn't say essential, but it is really something that reviewers look for. Reviewers do not like one-tailed test under any circumstance because they think it's kind of like you're making it easier to reject the null with a one-tailed test. They think you're manipulating the data with a one-tailed test. So if I'm publishing something, I really want a two-tailed significance test. Even if it makes sense to be one-tailed, publishers, reviewers like two-tailed tests for everything. But I'm just giving you both scenarios here, because they're both viable scenarios, right? Okay, so let's move on to the mistakes we can make. So we are going to compare our significance level and our significance level is also known as our p-value. So in SPSS, you'll see p-value. It'll say p equals something. That is our significance level. What is that exactly? This is the probability of getting your result, whatever the sample, right? That's from the sample. Or a more extreme result, which is also something you'd want, right? You'd want something further in the tail. The probability of getting your result that you got in the sample, or a more extreme result, a bigger result, a better result for you, if the null hypothesis is true. So that p-value gives you the probability of getting a result that you got, or a better result, if the null is true. We generally set this, our comparison value is our alpha. This is comparison value. This is alpha. To reject the null. If your p-value is less than alpha, alpha is typically .05. If your p-value is less than alpha, you're going to reject the null and support the alternative. So when your p-value from running an analysis is less than 0.05, in some cases, very conservative cases, it could be 0.01, but in psychology, it's almost always 0.05. In medical research, you could maybe make it 0.01 because you're afraid of making a mistake. It's going to cost a lot of money, it's going to get you sued, etc. But 0.05 is typically what it is. If your p-value is less than its alpha value, you're going to reject the null. If it's not less than alpha, you're going to fail to reject the null. And those are basically the rules. Now, what is alpha exactly? It's a comparison value. It's also, alpha is the probability of a type 1 error. So now we have type 1 error, and this alpha value is the probability of making a type 1 error. What is a type 1 error? Type 1 error is rejecting the null when the null is true in the population. So remember, we're testing a sample. So we're making a decision based on our sample about the population. If I reject the null in the sample and the null is actually true in the population, I've made a type 1 error. I've made a mistake. I've incorrectly rejected the null. That is type 1 error. Incorrectly reject the null hypothesis. Okay, so I reject the null in the sample, and the null is really true in the population. It is usually 5%, this error rate. And we don't want to lower it too much, because if we lower the alpha value too much, we increase something called type 2 error. So type 2 error is known as beta. Beta is the probability of type 2 error. And this is the probability of failing to reject the null when the null is false in the population. So these are different types of error. So type 1, we reject the null in the sample, but the null is actually true in the population. So we've incorrectly rejected the null hypothesis for type 1 error. Type 2 error, which is beta, is when we fail to reject the null in the sample, and we should be rejecting the null because the null is false in the population. So we should be rejecting the null in the sample, but we don't. And we incorrectly fail to reject the null, right? So in type 1 error, we incorrectly reject the null in the sample. In type 2 error, we incorrectly fail to reject the null. We should be rejecting the null because the null is not true in the population, but we don't for a variety of reasons. If you increase type 1 error, right, you decrease type 2 error. If you increase type 2 error, you decrease type 1 error. So we might be afraid of type 1 error and we lower it, well, then we increase type 2 error. And the problem with type 2 error is there are a lot of things that work. So your idea works, the treatment works, the drug works, but you can't find that in the sample. So the treatment is working, but based on the sample, you can't tell that. You think the treatment's not working. And so then you shelve the treatment. You say, oh, this treatment doesn't work. Let's try something else. When in reality, if you had the entire population, you would find out that your treatment actually works. So this is a really frustrating problem because you have a good idea, but you just can't find the results of that good idea in the sample. And the worst part of it all is you don't know this is the case. You don't know if you're making a type 2 error. You just move on with your life and you try something else. You design a different experiment. You try a different drug. When the drug or the treatment actually works for you. You just never know that. And there's a lot of good research that goes to waste because of type 2 error. We're so afraid of making this type 1 error and coming up with a fake result, a false result, that we end up not finding true results or results that should be found. So if we lower type 1 error, we increase type 2 error, and that's why we kind of balance it off with 0.05. 0.05 is kind of a happy medium. Now, if we want to look at the decision tree, or decision box, basically. And my drawing is not great here. So this would be population. Null is true, null is false, right? And then we have sample. And we can have reject the null or fail to reject the null. Those are our only decisions. So when I reject the null, in the sample, right? So I'm supporting the alternative. And in the population, the null is false. That I'm making a correct decision. Also, when I fail to reject the null, so I cannot support the alternative because I failed to reject the null, and the null is true in the population, I'm also making a correct decision. Now, when I reject the null in the sample, and I've made a mistake because the null is true in the population, I've made a type 1 error. That is equal to alpha. And then if I fail to reject the null when I should be rejecting it in the population, then I've made a type 2 error. And that's beta. And that's kind of our decision matrix. Now, we don't know if we're making a type 1 error or a type 2 error. We know the probability of making a type 1 error because that's our p-value. The probability of making a type 1 error is our p-value. So if you see p is less than 0.001, that means there's a very tiny percent of chance that we're going to make a type 1 error. It still exists. Like, we can never be 100% certain of anything. It's all based on probability. So you can have p equals 0.000001. You're pretty much almost certain that you're doing the right thing, that you're correctly rejecting the null. But there's still that fractional, tiny probability that you're making a type 1 error. The best thing to do is get a big enough sample so that your p-value, your probability of getting the result you got, is really small. Because that's the probability of type 1 error. You want the probability of type 1 error to be as small as possible. And the best way to do that is get the sample bigger. Now we have this concept of power. Power is the probability of correctly rejecting the null hypothesis. Now, this is important because as a researcher, my goal is to reject the null hypothesis. And power gives me the probability of correctly rejecting the null hypothesis. Let me just put rejecting instead of rejection. There we go. Now, power is equal to 1 minus beta. So it's 1 minus the probability of type 2 error. That's equal to power. Ideally, you want power to be at least greater than or equal to 0.80. Greater than or equal to 0.80. That means you want at least 80%. You want at least an 80% probability of correctly rejecting the null hypothesis. That means rejecting the null hypothesis when the null is actually false in the population, when you should be rejecting it. You want power to be greater than or equal to 0.80. You want at least an 80% chance of finding a result. So think of this. This is finding a result in the population, finding that result in the sample. So I want at least an 80% chance of being able to find a result in my sample if the result really exists in the population. Now, why is that a problem? Well, samples are not always the same as populations, right? You can have a better sample or maybe not as representative of a sample. So that's why I want this power to be greater than or equal to 80% or 0.80, because at least I have an 80% chance of finding the result in my sample if it exists in the population. And that's the goal. The goal is always, if this hypothesis should be supported, if it's occurring in the population, whatever you're looking at, you want to be able to find it in the sample because we can't test the entire population. if we can't find a result in the sample, we're in trouble, right? And now the best ways to increase power to ideally 0.80. The easiest way is increase n, which is your sample size. So increase your sample size. This is by far the best way to increase power. You want to get a lower p-value. You want to be more certain of your result. You want to more easily reject a null hypothesis. Increase your sample size. Get as many people as you can. Reduce variability. That's a lot harder. Can you reduce the variability? You can, but it's difficult because measuring something in psychology is not like measuring things in physics or chemistry. There's a lot of variability when we take a measurement of pretty much anything. There's no real physical measures in psychology per se other than reaction time. But there's lots of error in measurement in psychology. So to reduce the variability, you have to come up with better measures of whatever you're looking to study. And that's easier said than done. It's hard to do that. You have to improve on whatever scales are out there, or improve on whatever intervention and the measurement of that intervention that you're doing in your study. And so that's a lot harder than increase sample size, increase n. You can also increase alpha, although, as I said, if you increase alpha, you're also increasing type 2 error. So you'll increase power by increasing alpha, but you'll also increase type 2 error. And that's probably not a good trade-off. So we really don't want to play with alpha too much. We want to leave it at 0.05 as much as possible. Plus, you can't publish anything that's over 0.05. Like you could say, oh, we increased alpha to 0.10 instead of 0.05, and you're going to try to publish that, someone's going to reject it. You can't do that. Reviewers want 0.05. Bottom line. So these are all ways you can try to increase power, but the easiest way is increase n. That's going to increase power. So that's kind of the basics of power and the basics of type 1 and type 2 error. Now we're going to move more into hypothesis testing here. So previously we did a single sample z-test. I mean, a single score, I should say. Sorry about that. Single score z-test, where we compared an individual score. So we had something like this. Z is x minus mu over sigma. X was our individual score. Mu was the population mean, and sigma was the population standard deviation. This works well with a single score. A lot of times you're not using single scores, though. You're using samples. So if I'm testing a hypothesis with a sample, I'm going to use something called the one sample z-test. My arrow looks like a 7 here. Sorry about that. That's really an arrow like that. Z is equal to the mean of the sample minus the population mean over the population standard deviation divided by square root of n. This denominator is called the standard error of the mean again. We talked about this previously. Standard error of the mean. So whenever I'm using a sample mean, which is m, and I'm comparing it to a population mean, if I'm using a sample mean, I must use a standard error in the denominator. And once again, look at the n. As I increase n, what's going to happen to the denominator? If I increase n, then this denominator is going to be bigger, right? And then sigma over a bigger number is going to be smaller, and therefore our z is going to be larger. So by increasing sample size, I indirectly increase the value of z, which is one way to increase power, which is the probability of correctly rejecting the null hypothesis. So we're going to work through problems using a one sample z-test. Now, need to use z when you have the population standard deviation. So if you know the population standard deviation, you are going to use z. This is sigma, by the way. The population standard deviation is sigma. So if you know sigma, you're going to use z. If you don't know sigma, right? So otherwise, if sigma is unknown, you need to use t, the t distribution. But if we know sigma, we're going to use z, and that's what we're going to focus on today. Now, in reality, do you know the population standard deviation in research? Probably not. You probably don't know it. The only way you would know the population standard deviation is if you're dealing with something like the census, where there's years worth of data on pretty much everyone in the country, right? The census is pretty thorough. It's not a sample. It's a giant, giant mass of people living here. Pretty much almost everybody living here is supposed to be in the census. So we're getting population-based data from the census. Or if you have historical data. Let's say I taught this class for the last 20 years, and I've saved all my data for the last 20 years. I probably could tell you the mean on exam 1 for the last 20 years on average, and the standard deviation. So I have historical data that I can compare it to. Then I can use sigma. But if I'm doing research on a population that I have no knowledge of, and I don't have most of the population data on me, then I have to use t because I will not know sigma. So in 90-something% of cases, you're not going to know sigma in research. You're going to have to use t instead. But for now, for these kind of problems, we're going to assume that we know sigma. So now I'm going to open up the problem bank that I have under chapter materials. And we're going to go into worksheets. I'm going to look at one sample z examples here. Let's take a look at this. So we're using 0.05 to test this hypothesis. So I'm going to move this up here. Okay, so this is the problem we have here. I don't know why there's some of these question mark issues going on. All right, but I can, it seems like it's mainly the for some reason, the T or the TI is being replaced. So yeah, it looks like TI is being replaced. So I'm going to fill in the TIs here instead of these question marks. I'm not quite sure why that's doing that, but TI is coming up as this. It's not reading it correctly. So I'm just replacing TIs to make it clearer. More TIs here. It'd be nice to just copy and paste things, but every program's got its own issues with things. So I'm just replacing TI so we can all read this like that. Okay, on the basis of her newly developed technique, a student believes she can reduce the amount of time treating schizophrenics spent in an institution. Okay. As a director of training at a nearby institution, you agree to let her try her method on 20 schizophrenics. So that's our sample, right? So I'm just going to write N as 20. That's the sample size. Randomly selected from your institution. The mean duration that schizophrenics stay at your institution is 85 weeks. So that's the mean of the sample. And the standard deviation is 15. So that's my sample standard deviation. Well, that's my population standard deviation. Actually, that's the population. Okay, so these are population values, so let me erase that. So the mean of the population is going to be 85. And the standard deviation of the population, because your institution is the population. So that's going to be 15. Now our sample, the scores are normally distributed in the population. The results of the experiment show that the patients treated by the student stay a mean of 78 weeks. So in our sample of 20, treated by the student, that's the key right here, treated by the student. So you know that's the sample. And the standard deviation of the sample is 20 weeks. Now, if we know sigma, which we do, then we don't need to look at 20. If I know the population standard deviation, I'm going to use Z. And if I use Z, it doesn't matter what my sample standard deviation is. So I can just ignore the 20, right? Here is our null and alternative. So null would be there's no effect. The new technique has no effect on duration of patient stay. No effect on the duration of patients that stay. Now our alternative, is it going to be directional or non-directional? Well, we have here reduce. So you see the word reduce? Reduce means directional. So the new technique will reduce. We know that's a one-tailed test because it's a directional term. So it's a directional hypothesis. Reduces duration of patient stay. That should be S apostrophe. With the apostrophe there. Okay. So this is a directional hypothesis because we're talking about reduce, make less. So we're looking in the left tail only. So now we're going to compute the z-score. Mean minus mu over sigma divided by square root of n. Our mean here is 85. Our mean of the sample here is 78. Mean of the population, which is mu, is 85. The standard deviation of the population is 15. And the sample size is 20, so it's going to be square root of 20. This is going to be negative 7 over 15 divided by square root of 20. So I don't have the square root of 20 exactly posted or exactly in my head. So I'm going to use R to find the square root of 20. Once R decides to load for me. Okay, it's loading. I wish it would not have to load, but it always does. And if you have your calculator out, you can do square root of 20. It's really going to be a 4. It's going to be 2 radical 5. I don't know what that is, though. Square root of 20 is going to be equal to 4.47. So this is 4.47. So this is -7, and now we got to do 15 divided by 4.47. .36 rounded to 2 decimal places. 3.36, that looks right. 3.36, and now we're going to solve that. -7 over 3.36. -2.08. So it's in the right direction. We want negative, right? This is our distribution. Here's 0. It's a little crooked. Don't mind the crookedness. -2.08 is down here. Now remember, if we're using alpha of 5%, then I want the result to be in the tail here, 5% in the tail. Okay? So we need to find the probability in this tail, and it's got to be less than 0.05. And we can actually find that probability by looking at our table. And our table here is under the study guides, right? We have table 1 still here. And we can look up our t-value 2.08 in the table and look for column C. And when we do that, we get this value, 0.0, doesn't want to highlight for me, 0.0188. So the P here, our p-value, 0.0188. Is that less than 0.05? It is. So since P is less than alpha, 0.0188 is less than 0.05, we reject the null. And we support the alternative that the new technique reduces duration of patient stay. Now, this is the exact probability of a type 1 error. So basically, what this is saying is this -2.08 or a greater negative value to anything to the left of -2.08, right? That the probability of getting this result, if the null is true, is 0.0188. That's a very small probability. Since that's the probability that the null is true, we're going to reject the null. And we're going to support the alternative. So 0.0188 is less than 0.05 alpha, and we reject the null. If it was not less than 0.05, we would fail to reject the null. Now, you don't have to use the table values. If we're looking at 0.05 and 0.01, there are set values in the Z table. And we can actually see them in the Z table at the bottom of the table where it says infinity. Does it give me infinity? No, it gives me infinity in the T table. Okay, so I can't show it to you in the Z, but I can show it to you in the T table when we get there. But these are the values. So instead of looking up column C here, we can, this gets you the exact p-value, but we can do a different, use a different shortcut here. So this would be critical values of Z. So we're going to compare our Z-scores to these critical values. When alpha is 0.05, when alpha is 0.05, one tail, right? What do we have? We have 1 point plus or minus 1.645. That's our critical value. So if our obtained value is greater or lesser, more extreme than our critical value, positive or negative 1.645, we're going to reject the null. So negative 2.08 is more extreme than negative 1.645, so we would reject the null that way by using this critical value. So our alpha of 0.01, one tail, is plus or minus 2.33. Now we're going to do it again with 0.05 two-tailed. This is one-tailed still. Two-tail is going to be plus and minus 1.96. So when you have two-tailed, you have two critical values, a positive critical value and a negative critical value. And then for 0.05, 0.01 two-tailed, and these things you should memorize because they're going to be on the exam, and they're easy ways to do the Z problems. These only apply to Z. Plus or minus 2.58 is our two-tailed probability values. And these four values you should try to remember if you can. Okay, so let's move on from that. Let's move on to the next problem. That's good. Let's see where the next problem is here. Have to get out of this table, go back to worksheet. More one sample Z. Here's another one. University president. Problem with the white space is sometimes the formatting is like here again. Once again, I have this thing instead of TI, I have a question mark. Okay, so university, and I got this random line here for whatever reason. I got to erase it somehow. The university president believes that over the past few years, the average age of students attending his university has changed. So that's a word, keyword here, changed, right? That's important because there's no directional term here. Change means either plus or minus, increase or decrease. So right away, that's two-tailed. A two-tailed or non-directional test. To test this hypothesis, an experiment is conducted in which the age of 150 students, so that's our sample size, have been randomly sampled from the student body. The mean age is 23.5 years. That's the age of the sample. So the age of the sample is 23.5. A complete census taken at the university for a few years showed a mean age. Now that's the population because it's a complete census. So that means historical data. The mean of the population is 22.4. And the standard deviation of the population is 7.6. We know sigma, so we can use Z. So here's our Z again. And we plug in mean of the sample is 23.5. Population mean is 22.4. Sigma is 7.6. Square root of n is square root of 150. And we simplify this. 23.5 minus 22.4 is 1.1 over 7.6 divided by square root of 150. So I have to go to my cloud, my R here, square root of 150, 12.25. You might have some rounding error, which is fine. 1.1 over that fraction, 7.6 over 12.25. Gives me 0.62 rounded to 2 decimals. And then 1.1 over 0.62. 1.77 rounded to 2 decimals. Positive. So there is an increase, right? You see it here. It's 1.77. So now we have to determine, should we reject the null. So the null here is the average age of students. The average age hasn't changed. That's the null, no change. The alternative is non-directional. The average age, just you could write of students if you want to be more specific. I'm just writing this because it's hard for me to always write with the tablet. Has changed. Something simple like that. This is non-directional. It's a two-tailed test. We get 1.77. We need to find the critical value. So I can look this up in the chart, but we can also rely on our critical values. And remember, we're using alpha. Let me check the alpha level here. What alpha are we using? We're using 0.01. Oh, wait. No, that's not. It's a different problem. No, we're using 0.01 to test this hypothesis. 0.01 this time, and we're using 0.01 two-tailed. So the value for the critical value for 0.01 two-tailed or non-directional is equal to plus and minus. You have two. Two-tailed means two critical values, plus and minus 2.58. So now we're comparing our value 1.77 to 2.58. So I'm going to draw the curve. Here's 0. Here's our first critical value, positive 2.58. And our negative critical value is negative 2.58. We need both of them because we have two-tailed test. The 1.77 falls here in the body of the curve. This obtained value needs to fall in the tails that are delineated by the critical values for us to reject the null. So if this number fell in the tails here, we'd reject. But since it falls in the body, we fail to reject. And the average age of students hasn't changed. So all I did was I wrote my critical values out. I found my obtained value, 1.77, and my obtained value is not more extreme or in the tails delineated by the critical values. So I failed to reject. Let's take a look at the next one. Gasoline manufacturer. Okay, here's the next problem. Okay, I don't want to do that. I'm just getting rid of the question marks that are showing up here for whatever reason by putting TI in this place. Gasoline manufacturer believes a new additive will result in more miles per gallon. So we see more here. That's going to be directional. So our null, new additive, New additive does not increase miles per gallon, and our alternative is the new additive increases directional hypothesis miles per gallon. What do we have here? The results show a mean of 247 miles per gallon and a standard deviation of 4.8. Okay, so our population mean, so this is historical average. Population mean is 24.7. Standard deviation of the population we know is 4.8. Once again, we know this because we're taking historical data here. And then our sample is 75. The sample mean is 26.5. And we don't know the sample standard deviation. It doesn't matter because we know the population standard deviation. So we need Z. Z is mean minus mu over sigma divided by square root of n. 26.5 minus the population mean is 24.7. That's the historical average. And the 26.5 is the new sample, the new additive. The historical standard deviation is 4.8. And we're square root of 75 here. So this is 1.8 on the top. 4.8 over square root of 75. 4.8 divided by square root 75. I'm just double checking. 0.55 rounded to 2 decimal places. So this bottom is 0.55. 1.8 over 0.55. 3.27. There's our Z value. Now, this is looking at what alpha. What alpha are we using? We are using 0.01 again. Directional 0.01. So I know that critical value alpha is 0.01 one-tailed. That value is 2.33 or negative. But since we're hypothesizing an increase, it's going to be positive. We're looking in the positive tail because we're looking for an increase. Here's our curve. Here's 0. 3.27. Our critical value is positive 2.33. It's right out here. Our obtained value is 3.27. It's in the tail, right? It's more extreme. Since 3.27 is in the tail, that's distinguished or set off by 2.33, the critical value, it's more extreme than the critical value. We're going to reject the null and claim that the new additive increases miles per gallon. And that's pretty much how to do the one sample Z test. Now, there's also something called effect size. This is basically the effect of the treatment / independent variable without regard to sample size. So it's basically the effect of the independent variable not looking at sample size. So the true treatment effect. The effect size, the sample size can push things towards significance or push things away from significance, but this is looking at the effect independent of sample size. So we use something called Cohen's d for a test like this. And it's equal to, so Cohen's d would be equal to the mean difference on the top, so m minus mu, and the population standard deviation on the bottom. So you see no sample size in here. So you then can look at what we have here, which is 26.5 minus 24.7. Divided by the 4.8 without the n involved. And you're going to see this is 1.8 over 4.8. Now this is going to be a lot different because, you know, we don't have 75 as our sample size, and that 75 is help pushing this towards significance. So 1.8 over 4.8. And we get 0.375 as our effect size. And depending on your values for Cohen's d, I don't know exactly what the text talks about Cohen's d. I have it in the slides, though. Everybody's sort of understanding of Cohen's d might be slightly different. So if we look at Cohen's d in the slides I provided for you under Chapter 8, there's a nice table here of Cohen's d. It's over here, Cohen's d. Right here, Cohen's d. Magnitude of d, 0.2 is small, 0.5 is medium, 0.8 is large. We're at 0.3. So we're between small and medium. I would still consider it small effect size. And that table is a good table to use as a reference. 0.2 is small, 0.5 is medium, 0.8 is large. 0.2, small. Anything less than that, right? 0.5, medium. 0.8, large. And that gives you a measure of effect size. So this is the effect of the treatment regardless of the sample size, ignoring the sample size. And that's important because you can have significant results with very small effect sizes, and so it's not a very powerful manipulation. It's not an impressive result. This is small to medium, so it's okay. It's not terrible. The treatment, the new whatever they're using here, seemed to work. Not tremendously because it's only 0.375, but it worked okay. It's not like down at 0.1 or 0.0 something. It's not being driven to significance by just the sample size. So that's important to notice that. A lot of editors and reviewers are going to want effect size moving forward. This has become more popular to report in the, when you're trying to publish. So that's it. So hopefully that made sense. If you have any questions, let me know. If not, I'll see you back online for our next lesson shortly. Bye for now.